how to calculate that or put that on. All right, here we are on page 45, and we're going to talk about a different way of doing probability. This material helps us to do some theoretical calculations. In general, there are three approaches one generally used to find. One is experimentally or graphically. Or you might argue it theoretically based on what describes the situation. But finally, what we're going to talk about today is moment-generating functions. And moment-generating functions come from physics, probably mechanics, University Physics 2 or 1, where you talk about moments about the mean, and second moments, like how objects twist and turn.
More statics.
Oh, more statics? Okay, statics.
I also did that. EFIS 1. No. Yeah, that was in EFIS 1.
Now, this is particularly useful when the function is a linear combination of random variables. Remember the motivation for we talked about when we talk about graphics is that we need to look at a shape, center, spread. And so having the mean and standard deviation does not distinguish what your probability distribution is. There are many distributions with the same mean and same standard deviation. So we want to have some way that we can distinguish persons from the other. Almost like your DNA, but not quite. Does not distinguish it from your identical twin, but kind of the same idea. You want something that distinguishes. Is there anything that does distinguish you from? Your fingerprint does? Do identical twins not have the same fingerprints?
I think I researched it, and it was like 1 in 50,000 chance that you have the same fingerprint.
Anybody off the
street? Or is
street?
that a fingerprint sensor?
Okay. Well, I can imagine if a sensor could be that as well.
Yeah.
Okay. Well, of course, I shouldn't talk about the all your information is known by Google and everybody else. Okay, so the center then for a probability distribution, I mean, you talk about the mean, you can talk about the median, you can talk about the mode for the center. For the spread, what are some statistics we might talk about for the spread? Very good, the standard deviation. Any others? The range. The interquartile range was something you should know. Very good. And what about the shape? Is there a statistic for that? I mean, we kind of have a graphical statement, whether it's right skewed or left skewed. What did you say?
Skewness.
Yes. So, but is there any numerical measure that helps us out with that? There is. That's right. We're going to talk about today. And that's our good friend Kurt. Kurtosis is what we have. Now, before we move on to the rest of this part, we need to remind ourselves how to differentiate. Actually, kind of move over here. I'm just going to flip this over for now. What is the derivative of e to the 5x? 5e to the 5x. Very good. We're going to use this derivative again and again. And in some sense, this is motivated not just by moments in statistics. Yes?
On shape, what is the word before skew on the right hand side?
Right. Sorry. Right skew or left skewness. Those are terms you should be able to recognize from a graph, by the way. The other thing that's kind of motivating this is something similar to a Taylor series. Kind of similar to this in that a distribution will have a unique moment generating functions as well as a function having unique. Some functions have a unique Taylor series. Some continuous differentiable functions under certain conditions have a unique Taylor series. I mean, if it has a Taylor series, it's unique. So here's the idea, is that we have x equals 0, the probability is 0.1, 1, and those corresponding probabilities. What I'm going to do is I'm going to assign each probability to a number. So the first one I'm going to assign to is for 0, I'm going to assign this to 0.1 e to the 0. X, I guess. And then for 1, I'm going to assign this to 0.2 e to the 1x. And what will I assign 2 to? 0.3 e to the what? 2x plus 0.4 e to the 4x. Which is kind of curious, but not so much. So whatever your probability is, your x, whatever your value is, you're going to put it in the exponent with e and put the probability in front. In this case, what's the probability that x equals 5? 0, because there's no 5 going around. So I should put a 3 there instead of a 4. I'm not exactly sure. E to the 3x, because that corresponds to x equals 3. Now, let's see how we could do this to find the mean. The mean is just like, if we put in 0 in for x, if we plug in x equals 0, what will this sum up to? .1 plus 0.2 plus 0.3 plus 0.4, which is 1. And so that's the first thing, that if we plug in 0 in for x, we get 1, because that should be the sum of all the probabilities. Now, let's take the first derivative of this. Well, first of all, this is just a constant. I'm just going to throw that away. Here, if I take the derivative, I'm going to get 0.2 e to the 1 times x plus 0.6 e to the 2x plus 1.2 e to the 3x. And if I evaluate this at 0, this equals 0.2 plus 0.6 plus 1.2 2. And this is my mean. So what I have here written, I should have put the equal sign here. I should have crossed it off. My mean here would be 0 times 0.1 plus 1 times 0.2 plus 2 times 0.3 plus 3 times 0.4, and that does give me my mean of 2. So this is the first thing. If I take the derivative of my moment generating function, then I get the mean.
So this is first moment about 0,
Yes.
but then it's just the mean.
The first moment about 0, if you evaluate at 0, x equals 0, will give you the mean.
Well, the first thing we evaluated did not give us that. It was the derivative.
Yeah, that's right. So this is if we plug in 0 in, we just get 1, the sum of the probabilities. So that's why I have to cross off this equal sign.
So is the first moment about 0 equal to the mean?
Yes.
Which is so where did this expression come from?
Which one? The one on the right here?
The top one, the 0.1 e to the 0x.
Yeah.
Where did that? Because you took the derivative of that and you found that was equal to the mean, but where did the first thing come from?
That's just how we define what the moment generating function will be.
So the moment generating function is defined as what?
Oh, okay. I didn't give myself enough room here. Well, here, let's look at the second page. The moment generating function is the expected value of e to the tx.
Okay.
So I was giving you a little preview before I needed to. So let's do the second moment about the mean, and let's not use the moment generating function. I got too excited. I was just so excited to put the moment generating function that I wrote the moment generating function up here, and really I was just supposed to calculate the mean for you. Let's calculate the second moment about the mean. This is going to be, since 2 is the mean, this is going to be negative 2 squared times 0.1 plus negative 1 squared times 0.2 plus 1 squared times 0.3 plus 2 squared times 0.4. And I think if I do that, I get 1.0.
When x equals 2, wouldn't it just be 0 squared times 0.3?
Oh, it would be. And that's what I have there on my notes. And this would be 1 squared then for 3?
Yeah.
So change this to 0 and 1. So 0.4 plus 0.2 plus 0.4 does give me 1.0. And that's my variance then. I'll even put my little sigma squared there. All right, let's try the third moment about the mean. In this case, we're going to subtract x minus 2 cubed. So why don't you go ahead and calculate that. Go put in the 4 x values, cube them, multiply each of those times the probability, and we will calculate what that is. What value did you end up getting?
1.
You got 1?
Sure. That's something wrong.
Well, you could be right. What'd you get?
-0.6.
You did get negative 0.6, Calvin?
Oh, okay.
Did you get negative 0.6? You did? Josh, did you?
I did.
Okay. Well, I'll trust you then for that.
I see what you're saying.
I always trust myself. Okay. So if the first moment about 0 gives us the mean, which measures the center. The second moment about the mean gives us the variance, which measures the spread. The third moment about the mean actually depends upon the scale. So we're going to divide by sigma cubed to standardize. In some sense, you're getting rid of the units here. And so this measures the departure from do I want to say symmetry. In other words, the skewness of the data. So if symmetric, the kurtosis is What do you think? 0. That's right, because you have as much on the left as you do on the right. So there's a symmetry beside that, kind of. If negative, the distribution is left skewed or negatively skewed. Now you can see where the negative comes out. And if the third moment is positive, the distribution is right skewed. So we do have a statistic. It's difficult to interpret if I might show it other than if it's positive or negative, as far as the skewness of the data. Okay, can I move on to... Nope, I can't. Abby, what's the question?
Why didn't you go all the way from I 1 to 4?
Why didn't I?
You only plugged into the third moment. You only plugged in X equals 0, 1. I think you plugged in the number.
So we had 4 values, right? X equals 0. So if I put in 0 minus 2, I get negative 2, and raise that to the third power, I get negative 8. My second point is 1. 1 minus the mean, 2, gives me negative 1. Negative 1 to the third gives me negative 1. My third point was 2. 2 minus 2 is 0, so that cancels off. And my fourth point was 3. 3 minus 2 cubed gives me a positive 1, and multiply by that probability of 4. So most statistics, you try to have a graphical representation and numerical representation. Not always you get that, but the kurtosis kind of tells us whether it's right skewed or negative or left skewed. And it's one that you can ask most programs, including Minitab, what you get. So the kth moment about the mean, then, is the expected value of x minus mu k. And there's actually names for the fourth moment about the mean. And there's actually statistics for the fifth moment about the mean. It's sort of like the third derivative is the jerk. Is that right? And the fourth derivative is the what one? Snap? Yeah. Okay. And then anyway, so there's derivatives all the way through, and there is some interpretation for that, but it gets a little bit trickier. All right, so now I should give the moment generating function for our one on this one. What this is, the expected value of e to the tx. So e to the tx, t is going to be my variable, and x is actually going to be my numbers. Hallie?
So, what is a moment, and why did you only take the derivative for the first moment?
Well, because I was getting ahead of myself. The reason why we'll take a derivative is we're going to take the derivative of the moment generating function. The first derivative of the moment generating function evaluated 0 will give us our mean. The second derivative evaluated 0 will give us the second moment, which we can use to calculate the variance. And the third
So you
derivative.
are taking the second derivative. So
We will, yes. I was just too excited to show you. And I like taking derivatives. They're great things. But unfortunately, I was a little out of step. Like, yeah, my dancing days. Wait a minute, can I dance now, or still I'm prohibited?
No,
It's out of way.
Sanctioned dancing.
Okay, sanctioned, or it's choreographed, right?
Or if it's designed to worship God.
Okay. See, choreographed, I'm still out of step, so. All right, let's go ahead and write out the moment generating function for this. So just a reminder of h of x times p of x. So what we would have gotten is e to the 0 times 0.1 plus e to the 1t, and that was 0.2, and then e to the 2t was 0.3, and 0.4 would have been e to the 3t. Because those were my 4 x values, 0, 1, 2, and 3, and in front gave me the probabilities for each one of those. So it exists if we can find some small tiny interval around the t value. Most of the time we plug in 0, but there are other times we can plug some other things as well. So now we get into some advanced calculus ideas of when such function exists. but you do get a moment generating function for this. So let's take the Bernoulli. What is the moment generating function when t is equal to 0? Well, if this is 0, I sum up all my probabilities, and that's just 1. So I'm just going to write that again, that mx evaluated at 0 is 1. That's kind of a good thing to know. And let's have you write out the Bernoulli random variable of a failure is 1/3 and excess is 2/3. So go ahead and write that out for the moment generating function for a Bernoulli random variable. So this is, even though moment generating function is odd on the test, you do have to be able to write the expected value of a function. So see if you can go ahead and do that. So I hope you got 1/3 plus 2/3 e to the t. Uh-oh.
I just have a question.
Sure.
Is it e to the t or e to the x?
It's e to the t because x will be the random variable you plug in.
So
x is 1.
Okay.
So when x is 1, this probability of 1 is 2/3. You get that. And obviously, if you take this derivative, you're going to get 2/3 e to the t. You plug it in. Your expected value, probability of success is 2/3. That's your average or expected value for that. So in general, the expected value of a Bernoulli random variable is q plus p e to the t, where q is equal to the failure 1 minus p. I just think q is much more nicer than 1 minus p, but that's okay. And from this, no, go ahead, Alex.
Maybe you mentioned this briefly, but where do the moment generating functions come from? Like, who looked at this and said, yes, that describes the mean when you take the first derivative?
Well, remember that the mean is x times e to the, right? The mean, the expected value is x times your probability.
Mm-hmm.
So they were thinking that, hey, if I take the derivative, I bring this x down,
Right.
plug in 0, I'm going to get the mean. It's sort of like what you're doing with the geometric series. That's what I'm trying to get you to do the geometric series on your take-home to kind of see that there's these patterns. Really, it comes from, look, if you work with moments in Newton, this would make sense to you because the balancing point is the mean, and that's the balancing point you have for a moment.
Oh, and then the second moment is like
The variance, and so that kind of tells you,
rotation.
yeah, gives you some sort of ideas of the rotations and things like this. So it follows, if you had that background in physics, this would be like, oh yeah, sure. But if you don't have the background in physics, like, where in the world does this come from?
Well, the introduction of the exponential seems
odd, but remember that the derivative of e to the x kt is just going to be k e to the t, so you get that k down.
okay.
And if you take the second derivative, you're going to get k squared. Hey, we have that formula, e to the x squared minus e to the x squared. That gives us our variance. And so it's sort of like,
Okay. Yeah, okay.
so here's the big idea. If the moment generating function exists and is the same for two distributions, then those two distributions are the same. This is the, I guess it's not You've Got Mail. It's the Hallmark Christmas story, right? It's like a third of the Hallmark Christmas stories. Like this guy likes this woman at work at the selling Christmas trees, but he also likes this girl who's online, and then at the end it turns out they're the same. So they live
That's
happily
every
ever after.
Hallmark movie. That's not a third. That's all of them.
All right. Anyway, so that's the idea at the moment generator.
I was engaged at the beginning. I didn't realize it.
I didn't realize I touched a nerve. Okay, I'm sorry. All right, what is the PMF, probably mass function, for this function right here? What are my random variable values that I need to be concerned about? 0, 1, and 3. That's right. And what's the probability for 0? 0.3. What about for 1? 0.2, and then 0.5. All right, now, this takes a little bit of work here for this next one. I don't think I have enough space in my little line here. So we're going to have to go to a blank. Go to the blank side of this. I'm supposed to write notes on this side anyway. So let's do the expected value of e to the tx for Poisson. So what this is the sum from x equals 0 to infinity of e to the tx, and then I put my Poisson distribution. You probably don't remember what the Poisson distribution, but it's lambda to the x, e to the minus lambda over x factorial. So this summation only has x's in it, so let's get rid of anything that doesn't have an x in it. Anything that I can bring out front? I can bring out e to the negative lambda out front. Let's go down, I guess. And is there any powers that I can sort of condense? I don't think I can condense anything with the factorial. Anything else that I can condense, especially teachers? Yeah, I can condense this lambda and e to the t. So I'm going to get lambda e to the t raised to the x power. But from Taylor's series, what is it when you have summation of the x over x factorial? Say a little louder, Mitch. Taylor series spans. This is our series. I mean, this is. It's e to the what? It's e to the something. It's e whatever is in here. It's e to whatever that is in here by the Taylor series. I'll just quickly go over here to the Taylor series that e to the z is equal to 1 plus z plus z squared over 2 factorial plus z cubed over 3 factorial plus z to the 4th over 4 factorial. Dr. Thompson, remember? For those of you who had Calc 2? So what this is equal to is e to the lambda e to the t. And I can simplify this by taking the exponents added together, and I'm just going to save a step and factor out a lambda and get e to the t minus 1. Bitch.
Why is it going from e to the tx to e to the t to the power of x?
Well, so like this x here, this is the same thing as t times x is the same thing as like e to the t to the x. And so then you can put those together. See, those teachers in 9th grade algebra, There's use. Now, from this then, we could calculate what the mean is and what the variance is. Take this derivative with respect to t, plug in 0. Take the second derivative with respect to t, plug in 0, and that'll give, well, then we'd have to subtract it from our mean squared. And we may do that. I don't know if we're not going to have time. But that's one thing that we have. Once we have this, we can now calculate an easier way, rather than changing summations and doing changes of limits of summations. We can just take the first and second derivative, use our shortcut formula for variance, and find out what the mean and variance are. Let's go back to our original program. The first derivative, that is, x2 whatever, is equal to whatever derivative you have of 0. So, for example, you take the derivative of the moment generating function and take this derivative with respect to t, what you end up getting is the summation of x e to the tx p of x. And at x equals 0, this is equal to the summation of x p of x. Okay, let's take the second derivative of e to the tx. Now we have to do a little bit more work because we have to use the product rule. No, we're taking the derivative with respect to x. No, we don't have to do too much. So e to the tx, the derivative of e to the tx with respect to t is x times x. I'll just make it x squared. E to the tx p of x. At x equals 0, this is equal to the summation of x squared p of x, or e of x squared. I'm sorry, yes, you're right. T equals 0. T equals 0. I apologize again. This actually is a very nice shortcut formula. If you let h be the natural log of the moment generating function, then the expected value is just the first derivative of your 0 and the variance. Let's do the Poisson then. H of t will be the natural log of e to the lambda e to the t minus 1. And what's the natural log of a function of e? Cancels out, so I get lambda e to the t minus 1. Then h prime of t is, well, lambda e to the t. And so h prime of 0 gives me lambda. Oh, sorry. So if this is, I take the natural log h prime of t, just remember we're taking it with respect to t, so it's minus 1 doesn't stick, and so h prime of 0 is lambda. So the mean is lambda. Also, the second derivative of t is equal to lambda e to the t, and so h double prime of 0 gives me lambda, the variance. What did you not get? Is that what you got?
No, I said, no, that's cool.
That is cool. And there's one other cool thing about the geometric distribution, but we will not. Oh, we have one little thing about the geometric distribution. Actually, it won't be the geometric, it's the binomial distribution. So remember that the Bernoulli is Q plus e to the t, p e to the t, right? So this is the Bernoulli. If we raise it to the nth power, this is the binomial. Because all we're doing is just taking the product of the various moment generating functions. And if you took this derivative and set it equal to 0, you could find the mean and also find the other thing. Actually, if you took the natural log, this would also be easier. And the geometric series, it's also easier to calculate its mean and variance by using the moment generating function from this. So it's a very nice theoretical tool. It's not as good in practice, but theoretically it's much easier to calculate what means and variances and kurtosis is for different distributions are. Yeah, it's not really heavily, Jonathan, they say not to overly study the moment generating function, but it does come in handy when you can't forget something. Okay, have a nice weekend. You might connect with your teammates either in person or via Zoom. And then,
What exactly is kurtosis? I think that's
Yes.
kurtosis is just a numerical measure of skew. That's it. So it's the third moment about the mean divided by the third power of the aggregation.
I have tabs at home.
Positive is right.
I don't know if it's
It's 0 there.
Yeah. Yeah.
Almost just drink.
It's all done, you know?
Right. Do we want to look over each other's write-ups? That's the only other thing I'd say would be less than
But I have tabs at home.
Yeah.
that would, I think that could be
On the benefit of living like 5 to 10 and having a lot of shops.
She should be, but she's not here today.
Can I ask you a question? Are you teaching math tech over daytime? Huh?
Go get coffee.
You're waiting one more year? Okay.
Saturday 3, right?
Okay.
Gosh.
I have a freshman on my, well, she was hoping to be able to travel for 2 daytimes. But if it's next year, she's only going to be able to do one. So she
I don't
was
know, but
asking
it
about
sounds
it.
like a sad one.
No, you're good.
People who don't like coffee.
Yeah.
That's weird.
Yeah.
Love coffee.
I feel old.
So good. I don't know if that's an addiction talking or the
Did you have any problems with any of the
enjoyment of
equipment?
drinking coffee.
I did
I
not.
don't know.
Good.